only noise. So now I want to talk about my in open problem session. So I want to talk about the general construction of unitary T design from spherical T design. So recently I have some problem related to the quantum design, quantum T design. So then I study about quantum T design and related topics, unitary T design. So related to the unitary T design, I found one open problem. So today I want to explain that problem, but I think this is extremely difficult and slightly different from the main interest of this community. This is much more oriented to the combinatorics. So firstly, I will explain the spherical T design and quantum T design. Then later, I will explain unitary T design. And we discuss construction of unitary T design, and we explain the two conjecture. And I explain the relation between the two conjectures. So firstly, what is the spherical T design? Spherical T design is this one. So f is a polynomial with d plus 1 variable with degree is t. So now we consider d plus 1 dimensional sphere. So no, dimensional sphere. D-dimensional sphere can be regarded as a d plus 1 vector element. So vector space. This is subset of the d plus 1 vector space. And we consider that polynomial. And we take uniform distribution on S subset S. So that uniform distribution, expectation of the uniform distribution equal to the expectation under the Hall measure. So this equation holds for any polynomial with degree D. So in that case, that subset is called spherical T design. So we consider its extension to the quantum case. Quantum case is we consider the dimension complex Hilbert space, and we consider normalization, and we consider its subset S, and we take its relation. So here is the Hall measure on the pure state, set of pure states, and we have that subset, and we consider uniform distribution on subset S. So we consider this equation. If that equation holds, then we call S is a quantum T design. So as you know, that kind of quantum T design can be constructed by using the spherical 2T design. So we choose subset S is a spherical 2T design. So in that case, for element S, we consider a vector in this way. So V is an element of sphere, and XV is a vector space. So this one, so normalized vector. So we consider that subset S prime. So S prime is quantum T design. So in this case, the matrix component of this one is a polynomial of degree 2T. So then, if S is spherical 2D design, then we have this equation. We have this equation. Then we can say that S prime is also quantum T design. So this is a very easy observation. So everybody can easily prove this one. But in the case of unitary, we have a more complicated problem. So we consider a UD. UD is a set of D times D unitary matrices. And we consider that subset. So we consider that subset, and we consider its average on this uniform distribution. So you consider tensor probability and tensor probability and complex conjugate. And that average equal to the average under the Hall measure on the unitary matrices. So M of dog. So we want to construct a good unitary T design from the spherical 2T design in this way. So firstly, we choose 2D minus 1 dimensional surface and subset. This is 2D design, and next one is 2D minus 3 surface, dimension of surface, and we take that subset and in this way. So from the next sequence of 2D design, we want to construct a good unitary design, but this is not so easy. So now we want to consider that problem. This is somehow complicated problem. So firstly, we need to make some connection. This is related to the problem of the how to say Grassmann manifold. So this is a sphere, and this is sphere and sphere for each element of sphere. So we have to define isometry map from R to J to CD. This is somehow orthogonal to this one. So this is very difficult problem. Firstly, you need to define F empty. F empty is a isometry map from the R to D to CD. This is natural one. So we choose natural isometry from the R to D to CD first one. And the second one, we need to define this one. But in this case, firstly, you already define this vector. So depending on this vector, this mapping should be defined as the image is orthogonal to this first one. Then third one is somehow similarly, we need to consider R to D minus maybe 4 to CD, such that the image is orthogonal to this one and this one. So using that in this inductive method, you need to define this isometric map. So using this isometric map, finally we need to define this unitary. So in this sense, we firstly choose this one. So this one is first one is the element of the 2D minus 1 sphere, and the second one is 2D minus 3 sphere. And based on this sequence of vector, we define unitary such that in this way, as this way. So because this one and this one orthogonal, and the second one and the third one is also orthogonal. So then this one forms the unitary matrices. Using this construction, we obtain the unitary matrices, and the this kind of measure equal to the measure on the each sphere, Hall measure. So this Hall measure can be decomposed to the measure on the each sphere in this way. So first one is conjecture one. Assume that the following subsets are spherical 2D design. We define in this way. So then this subset on the unitary set of unitaries is a unitary T design. So if this one is this one is a 2D design, then this one is a unitary T design. This is somehow one conjecture. So this conjecture means that using the 2D sequence of 2D design, we can construct a unitary T design. So this is very useful construction for the unitary design. So to prove this conjecture, we need to consider somehow very complicated mathematics. So to discuss that issue, you need to choose some sequence of index first. So K is some index 1, 2, 3, 4. And depending on K, you need to choose a sequence J1 to JT. So we need to choose 4 sequence, integer sequence J1 to T. Because please remember that in the case of unitary design, we need to consider matrix element of this. So this, in order to describe the component of this, you need to consider 4 sequence. Because input is somehow T times this one, and the input of this one is T times T sequence, and output is also T sequence and T sequence. So then totally we need to 4 sequence of T, 4 T sequence. So in order to identify each matrix component, we need to prepare 4 sequence. So one sequence is 1 to T, so J1 to T. So this is very annoying, but but in order to identify the matrix component, we need to prepare 4 sequence, and for each sequence, we need to define subset of this one. This subset is defined by in this way. So there is L. L is the element of 1 to D. So for each, then we need to identify the set of S, set of these indices. So the component equal, we need to correct the element of index S such that JSK equal to L. So we define this subset. Using that subset, we inductively define the function in this way. So G is a function. We need to define some function inductively, so this is somehow complicated. Firstly, G1 is always 1, and then second one is G2. G2 is defined by using this inductive method. So once G1 is defined, then G2. So GL defined, then you can define G plus 1. So using in this method, you can define function. So then there is another conjecture. That function GL plus 1 is polynomial with degree, this guy. Of course, the definition of G depends on the sequence of this integer sequence. So for any integer sequence, we can define GL, and for any sequence of integer sequence, this defined function GL plus 1 is a polynomial with degree, this guy. So if we can prove this conjecture, then we can prove conjecture 1. Because in order to prove conjecture 1, essentially the problem reduced to this conjecture 2. So because in order to prove the conjecture 1, you need to discuss for each matrix component. So each matrix component corresponds to this function. So in this way, it is enough to prove conjecture 2. So then now we have a problem. So how can this conjecture 2 is true or not? Indeed, this kind of problem already discussed by several persons. So indeed, 1 week ago, almost 1 week ago, I have a presentation about this conjecture. So in the Japanese conference about discrete mathematics, at that time, one author of this paper 5 attended, maybe this T. Okuda. So Banna is a very famous guy in combinatorics. But this paper has too many authors. I think some authors did not understand this difficult problem. They only contribute to the physics part, and maybe he is a very famous guy, but he worked on the experiment. I don't know if he's familiar to this mathematics or not. So many people, several people only focus contribute for the physical interpretation. But maybe some people, Nakata and Bannai and Okuda, they are very strong for the combinatorics. In particular, Professor Bannai is a very, very famous guy for combinatorics. In that paper, they did not construct in that way. They make much more somehow complicated method and somehow very unnatural construction for unitary T design. Then some Chinese guy found that he pointed out much better construction. But after that, we discussed with just that Chinese guy, we found that this kind of conjecture, we needed to prove that conjecture. However, 1 week ago, I presented that conjecture. Then at that time, this Okuda, Professor Okuda attended that workshop, and he pointed out that they already consider that difficult problem, and that problem is too difficult. So they could not solve that problem. So then they give up that method. Then they consider much more artificial, more not so natural method, unnatural method. So then they make some more limited method. Of course, this method is much better because we have a much more larger applicability than their construction. This is the story, a side story of our conjecture. So is there any question? So I want to stop my presentation now. Oh, there is a question. Huh? How, Niranjana, how are you? No. This is not a question, comment. So I forget to appoint ask the section chair. So then I have to make section chair by myself. So David, so please comment. David, no?
Yes.
Hello.
Can you hear me?
Yes, of course.
Great, thank you. I wonder, I may have missed it from the talk. How is the size of this construction compared to known bounds?
Compared to?
Is this particular construction close? Like, I think there are bounds on how big a unitary T design has to be. So I wonder how is this construction compared to how large a unitary T design has to be?
Because this is a construction. Essentially, this is no. Yes. This is a construction. So for firstly, we choose spherical 2D design in this one, and this is spherical 2D design, and this one design. So once we have a spherical 2D design, then we can identify minimum number for each spherical 2D design. Then combining with all this one, then we found the this number.
Okay. Okay, thanks.
Indeed, I also made some draft for this conjecture, but later I give up to make that conjecture because that conjecture already discussed by that guy. So. I think this conjecture and this construction is more efficient than their construction. But their construction is somehow complicated, so somehow limited, so somehow not so natural. 常に多さ、そう。Any comment or question or how do you think this conjecture or that topic? So if you are interested in this conjecture, so I can send a draft or this how to say PDF version and this one. Also, I have because I did not write explain the proof, but I also write down this proof for this theorem. So maybe there is no comment or other question. So then I want to stop my talk. Any other comment or question? Maybe nothing. So now, okay, today's session is finished now. So then I want to organize some discussion time, pre-discussion time. So now I open the breakout room. If you are interested in much more informal discussion, so you can stay here. But if you are very busy, so you can quit. So